So now section 4, we're talking about velocity. So it was position and time in the last one, now it's velocity. So we're kind of putting those two things together here. If the object is moving fast, if the object is moving slow, we kind of have a feel for that already. If the object is moving with a constant speed, this is an important phrase for us, uniform motion, okay? Constant speed, uniform motion, all right? We've got to keep that in mind. So take a look at the motion diagram here for the car and the bicycle. We have each second that goes by, the car moves twice as fast as the bicycle, so therefore the car is moving at a greater speed, right? So also notice that we have equal intervals of time, right? 0 second, 1 second, 2 second, 3 seconds. But we also have on our axis here, we have feet. So we know the time interval and we know the distance that's being traveled. So if we just look at the car, from 0 to 1 second, the car went 40 feet. From 1 second to 2 seconds, the car went from 40 to 80, so that's another 40 feet. From 2 seconds to 3 seconds, the car went to 120, so from 80 to 120, that's another 40 feet. So the car is moving 40 feet for every second that goes by. It has uniform motion, okay? So we have a distance traveled in an interval of time, and that distance that's traveled in that same interval of time each time is the same, therefore it's uniform motion, okay? Because it's a constant speed. Same thing is true for the bike. We went 20 feet, and then we went another 20 feet, and then we went another 20 feet each time in those 1 second intervals. So this is going 20 feet per second is what we would say, uniform motion. Make sense? Mm-hmm. All right, so let's move on. The greater the distance traveled by an object in a given amount of time, the greater that the speed is. And that should make sense to you already, given what you know of life, right? So this idea leads to this definition. Speed is the distance traveled in a time interval divided by that time interval. So how far did you go divided by how long did it take you to do that? Okay? So that leads us to sort of a formula. Your speed, which we maybe could give a letter to that, would be how far did you go? Yesterday we were talking about how far did you go as had a symbol to it. What was the symbol that we used?
Delta X.
It was delta X. And the time interval had a symbol also. What was it?
Was it like XT or
T.
X sub T?
It's T sub.
It's not just T.
Oh, T sub I.
T
And
sub
then T
F.
sub.
Yeah, both of them.
It wasn't just T sub I or T sub F. It was T sub F minus T sub I, which would make it delta T. The time interval is delta T,
Oh,
okay? From start to finish, that makes it delta T. So we now have a formula almost for speed. We'll talk about it a little bit later. The formula for speed is delta X divided by delta T, okay? So what is the speed of the bicycle? Well, we just kind of talked about it. The bicycle, let me kind of slide this back down so we can see it. The bicycle was, how far did it go? 20 feet, or 40 feet, or 60 feet, depending on what interval you want to use. So let's just say it went this far, which is 60 feet, divided by, what is the time interval in that distance that it traveled?
Would it be 3 seconds?
3 seconds.
So 20.
So divided by 3 seconds. Okay? And then that would reduce down. And we have 20 feet per second for the car, or for the bike. Now for the car, we can do the same thing. We can use the same interval of time, 3 seconds, right here, right? Now I'm not writing. Okay, there we go. Okay, so in 3 seconds, so for the car, how far did it go? 120 feet. And that reduces down to
40 feet per second.
40 feet per second.
What would that be in miles an hour?
we would do a unit conversion to figure out the miles per hour. We'd have to turn feet into miles and seconds into hours.
So you have to multiply.
And we haven't gotten to that point yet, so I'm gonna leave that for later.
So that's like super slow.
It's not that slow.
That's a good little pace.
So, what are the units? Well, feet per second, right? Because we were writing those, feet per second. Okay, so now let me go up here. The bicycles below have the same speed. How do we know?
Because they're both at the same, like, measurements after a certain period of
Constant
time.
speed, but just going different directions.
Yeah, the interval of time is the same. We can see that, right? 1, 2, 3, 4, 5, 6 seconds. And the dots are equally spaced for both, right? They're occurring at the same interval of time, the same spots. So 120, 100, 80, 60, 40, they're all lined up, right? So they have the same speed. Is it uniform motion? Is it a constant speed?
It's a uniform motion.
Uniform motion, yes. Constant speed, okay? Now, they're moving in a different direction. How do we know that?
Because it shows arrows of where it's going.
That's right. The arrows
Opposites up.
here are indicating but bike 2 is moving to the left, and here bike 1 is moving to the right. Also, we have the labels, 0 second, 1 second, 2 seconds, going in opposite directions, okay? So that's helpful. So let me write those down. We have dots equally spaced. Okay, we have the arrows, as we talked about, and we also have the labels for the seconds. So those three things are clues for us to tell us that the bikes were moving at the same speed, but opposite directions. All right, to fully characterize the motion of the object, we're gonna not only describe the object speed, but also the direction. So in that last example, we had one bike going one way, the other bike going the other way. So we need to talk about not just the speed, but the direction. So the distance traveled doesn't really capture any information about the direction traveled, okay? But if we instead use displacement, that does contain information about direction. So let me see if I can draw that out on the board. So if I start right here and I end right here, if I want to say the distance traveled, how far did I go?
We don't know.
We have no idea, okay? But what was my displacement? If I went from point A to point B, my displacement means
To the right.
from where did I start to where I finished? I went from here to here, and that's it, okay? But as far as distance traveled, I have no idea, okay? Because my distance traveled, I could have gone over here, and then up here, and then over here, and then down, and then over, and then hung out right here for a while, and then down here, and then finally over to here, okay? And then if I was on my in my car, I might have logged 171 miles on my car, and actually wound up only 1 mile away from my house in the end, okay? So my displacement would have been 1 mile, but my distance traveled was 173 miles. Okay? So these two things are very distinct, and we have to be careful about distance traveled versus displacement, because distance traveled is vastly different than displacement. Okay? All right. So displacement does contain information about direction. My displacement here was maybe 1 mile, and looks like if this was north, south, east, west, looks like I went like definitely east and then south of that, right? So I went south of east, okay? All right, so we have the ability to define velocity now, which is both speed and direction. Speed is great. We like to know how fast something is going. But we also like to know which way is it going, okay? And that's where velocity comes into play for us. We use velocity all the time. Sometimes speed is fine, but velocity is very important. We want to know which way it's going to. So velocity is displacement over the time interval. So displacement over the time interval. And that is our delta x over delta t which we just saw a little bit ago for speed. So speed is sitting here, delta x over delta t, but we also need to know what direction it went in addition to the speed, okay? So our formula will be v, let me change colors, v equals the delta x over delta t, but then we're also going to have to know what direction it was going, okay? Now this is the equation for average velocity. Instantaneous velocity is like you look down at your speedometer and you see that speedometer saying like 71 miles per hour. Okay, fine, that's your instant speed, okay? This is the equation right here for instant or average speed over the entire time that you were driving. So like if we took, 49 minutes to get from here to something that's 55 miles away, then we could figure out what our average speed was because we know the distance and we know the time it took us to get there. The distance and the time it took us to get there, okay? So that's an average speed. All right, it's critically important that you understand that a negative velocity means the object is moving in a direction opposite of what is defined as positive. So what is meant by that? Normally in a coordinate plane, we say positive x is to the right and positive y is up. Okay? Now if you define your axes normally like this and you wind up with a negative velocity, that means that you are moving against your normally defined positive direction. Okay? So if you're talking velocity and you are moving to the left in your normally defined positive direction to the right, then you have to say that you have a negative velocity. Okay? If you normally define your y-axis as positive up, but you're moving down, then you have to say that your velocity is negative. Okay? Now that's different than speed. Speed is always positive. If you're just talking about speed, then the speed is positive.
Well, you can't go negative. Like, you can be stopped, which is 0 speed, but it's not, you can't exactly,
Even if you reverse it.
even if
still
you reverse, you're still going
That's right.
back, the speed going back.
Put your
You
car in
can't go
reverse
negative
and
speed.
floor it, you're going to be going a positive speed,
just a different direction.
just in a different direction, okay? So your speed is positive, but your direction is the other way, right? So when we're calculating with velocity, if we get a negative answer, the negative sign is telling us we're going against the positive direction, whatever the positive direction was defined as, okay? And that is maybe the confusing part right now, okay? So we have to keep in mind what coordinate system we're dealing with, and also keep in mind, are we talking about velocity or are we talking about speed? Okay? So now the units of speed and velocity, really they're the same because this formula is the same, right? Like miles per hour or something, because we haven't started talking about meters per second like we should. Okay, so since we have distance over time, it makes sense that the units are a unit of length. So meters, feet, miles, divided by unit of time. So normally seconds, hours sometimes. So the velocity units could be miles per hour, meters per second, feet per second maybe, okay? Most of the time in this class, after we get rolling here, we're gonna be dealing with this one, meters per second. That's the unit we like the most in physics and really in the world. Because we're in the United States, we're kind of stuck in this ridiculous unit
We're not
of,
the only country that
we are
uses
like the only country, yeah. There's actually one other one, but you've never heard of it,
Really?
yeah.
it.
One out of.
Yeah,
Oh
it's
my
one.
god.
We're the
Isn't
only,
it in like Africa?
where is it? Yeah.
I know the country you're talking
Yeah,
about. I'm
yeah.
trying to remember.
I'm trying to remember too right now, I can't.
It has such a weird name.
Yes, I think it starts with an M. Maybe Liberia, and then, no, maybe there's three. I think Liberia is one of them, and us, and one other one that starts with an M, and it might be in Asia somewhere. I can't remember.
Mongolia?
No, it's not Mongolia.
No,
Literally
that's-
every other country uses the metric system. It's ridiculous. So we will use the metric system.
Alright.
So the word per, when you read these units here, so like miles per hour, meters per second, that word per, when you read those units, indicates the number of units required in the numerator for every 1 unit in the denominator. So we are doing a division there, okay? So it's how many of the miles do I have to go per every 1 hour that I'm going, right? Or how many meters have I gone for every 1 second that has gone by, okay? Or feet per second, how many feet did I go in 1 second? So if it was 40 feet per second, I went 40 feet in 1 second. If you think about it that way, that's pretty fast,
Yeah,
okay?
40
Like
feet.
I can't run that fast. I probably can't bike that fast. 40 feet in 1 second,
That's probably what, close
You're
to
moving.
20?
Really? Are you
20,
sure?
30 miles
you're
an hour.
moving.
Hey.
Okay, so let's see. Finding the speed of a seabird. So albatrosses are seabirds that spend most of their lives flying over the ocean looking for food with a stiff tailwind, which means the wind's behind, pushing along. An albatross can fly at high speeds. Satellite data on one particularly speedy albatross showed it 60 miles east of its roost at 3 p.m. and then at 3:15 p.m., 80 miles east of its roost. What was its velocity?
20 miles in 15 minutes.
Yeah.
Okay, yeah, so it went 20 miles in 15 minutes. What we want to do is
Oh my gosh.
Put 20 miles over.
start to learn how to draw a picture.
80 miles an hour.
So we're going to have its roost is over here, east of its roost. So we have, it started at one point, it was 60 miles away. And that was at what time? 3 o'clock?
3 o'clock, yeah.
Okay. And then at 3:15 p.m., it was 80 miles away. So here, 80 miles. And that's at 3:15. Okay. So now what we need to do is put this in terms of what do we know and what do we not know. So here at the first location, x sub I is 60 miles. Okay, and then t sub I is going to be what?
3 p.m.
No.
Yeah, 2 p.m.
No. Zero. At 3 o'clock is correct, but this is where we're going to start the stopwatch. And the stopwatch starts at 0. So this will be 0 what? What's the units
Zero
here?
H. Oh no, minutes. Do we want minutes?
We would say minutes probably. M-I-N for minutes, not M, because M is meters. Okay? Now, at the second position, this will be x sub what?
80.
X sub
80 miles.
X subscript
Oh,
is
F.
F,
Alright.
and the position is 80 miles.
And then T sub I,
T sub F.
T sub F
Equals
equals
15.
15.
15 minutes now.
That bird is going 80 miles an hour.
Okay, so now we're going to use our formula. We want to calculate its velocity.
F, X sub
So we're gonna
F
write
minus
V.
X sub I,
V equals,
X.
it's
sub
delta
F.
X over delta V, delta T.
Delta.
And that is X sub F minus X sub I over T sub F minus T sub I.
Equals.
Now, hold on. What do we know? We know X sub F, we know X sub I, we know T sub F, and T sub I is actually what?
0.
Okay, so this one
That's just T sub F.
is gone. Okay, so now we can plug in our stuff. X sub F was 80 miles minus X sub I was 60 miles
Over.
over T sub F, which was 15 minutes.
So that's 20 miles over 15.
So we have 20 miles divided by 15 minutes.
So that would be 4 miles every 3 minutes.
Well, you, yeah.
But could you go simpler than that?
Now, we're gonna wind up with units of miles per minute here, right?
Per minute. Oh.
Miles per minute is not a unit that makes a whole lot of sense.
This can be a decimal.
We would wanna turn it into miles per hour, yeah?
Oh, you moved your calculators.
Okay, so do the division, 20 divided by 15.
1.3, repeating.
1.2 miles per minute.
Okay, now that's not a very exciting decimal to work with, right? Now, I also said we're gonna wanna wind up with miles per hour, most likely, right? Right now we have miles per minute, so what we can do is a unit conversion before we do the division.
20 divided by 1.
We want to get rid of minutes.
Times about 4.
Times
So
by
to
60.
get rid of minutes,
Well, you have to-
we would put minutes on top here. We're gonna do unit conversions all the time in this class. Here's your first one. Minutes divided by minutes makes it go away. But what we're doing here is we're making an equal ratio here to get rid of the minutes and turn it into hours. So on the bottom is gonna be hours,
Yeah.
okay? Now, how many minutes are in an hour?
60.
So what we've done is
60
we've
minutes
made
over 1 hour.
like a fancy one here.
We did this in
Yeah, we did
chemistry.
it. We do it all the time. We do it in algebra 1, algebra 2, chemistry. We do it in this class. Okay, now we can reduce this in an easy way to make the math a little bit easier, okay? So notice that we have a bunch of fractions sitting here, and you can reduce these fractions on the fly before you type it into your calculator. Notice that 60 and 15 have a common factor in them of 15.
So that's 4 on the top.
15 goes into 15 one time, 15 goes into 60 four times, and now on the bottom, all we have is 1.
4 over 1.
On the top, we have 20 times 4,
80
5
miles
so it's
per
5
hour.
it's
which
5
is
miles.
80.
Oh,
80 miles every 1
And
hour.
now we have miles on top and hours on the bottom, so we have miles per hour as our units. It's 80 miles
that's
per hour.
cooking.
Yeah, that's quick.
Yeah, that bird's moving. Now, could we have gotten there without all of this process where we draw it out and label things and write down what we know and then use the formula and blah, 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 blah? Yes, because this is an easy problem, okay? But down the road, when we're doing problems that require a lot of stuff that we don't know how to do yet, it's going to be difficult if you're not doing this type of systematic, logical, methodical process using formulas and such, okay? That's why I'm going through this and I'm showing you how to be very methodical with the work, okay? Do it this way. I know you guys can handle this problem in your head. In fact, I heard you say what the answer was, just right off the bat. Yeah, I know, right? But write down this stuff, get used to doing it when it's easy so that you can do it when it's hard too, okay? All right, what do we got? One more problem maybe? Yep.
Yeah.
Okay, Jane starts from her house to take a stroll in her neighborhood after walking 2 hours at a steady pace. What does at a steady pace mean?
Constant speed.
Constant.
Constant speed, uniform motion.
Oh.
Okay? She has walked 4 miles and is 2 miles from home. For this time interval, what was her speed? Think about it, and then I'll ask you what the answer is.
Oh, okay, I get it now. Yeah, I got the answer.
What do you think?
It's B.
You think it's what?
I think it's 3, or B.
2 miles per hour.
2 miles per hour?
Because if she's traveled in 2 hours, she's traveled 4 miles
per hour.
Then you had to have traveled at least 2 miles per hour to get 4 miles in 2 hours.
What about this information right here?
That's just leftover. That's what's left.
You don't need it right
Don't need it, because we know that she's traveling at a steady pace
No.
for 2 hours, and she went 4 miles.
But then if it asked after, okay, so how long will it take her to get after those? How long will she have been walking after she gets home?
That would be like a
After-
follow-up question, right? So-
Then you'll need that information.
Exactly.
Right now we don't need.
Right now, we don't need it. For this time interval is just these 2 hours that she was walking at a steady pace. At a steady pace for 4 miles, 2 hours, the only possible answer is 2 miles per hour. Okay, so you had some useless information there that you didn't need to answer the question. 2 hours, went 4 miles at a steady pace, that's 2 miles per hour. Okay? All right, So the key phrase there was at a steady pace. Very important. All right, so that is it. We're done.
Questions we're doing on this.